Hello, today we are going to learn about vestigial amplitude modulation, how to generate Vsb signal, modulate it and demodulate it. So let's learn. So let's first learn what is amplitude modulation. So amplitude modulation is a technique which is used in communication systems wherein the amplitude of the carrier wave is varied in proportion to that of message signal. Now what does that mean? So let's consider this first signal as our message signal, which is colored in black. Let's consider the second signal, which is colored in blue, as our carrier signal. Now we can see that the frequency of the carrier signal is more than that of message signal. Now if we multiply both of them, the output is actually the red wave given below. Now we can see that the frequency of the red signal is actually equal to the frequency of the carrier wave, but the amplitude of the red wave is proportional to that of message signal. So here we can say that the amplitude of the carrier wave is actually modulated in proportion to that of message signal, and that is what we call it as amplitude modulation. Now, what are the different types of amplitude modulation? The first is double sideband suppressed carrier, the second is single sideband modulation, and the third is vestigial sideband modulation, which we are going to see in detail. Now, let's first see double sideband suppressed carrier. Now, let us assume our message signal as empty. Let us assume our carrier signal as cos 2 pi fct, where fc is actually our carrier frequency. Now, to modulate the carrier frequency, we multiply the carrier wave with the message signal. So, the output xt is actually mt multiplied by cos of 2 pi fct. Now, we know that from the Fourier properties, if we multiply two signals in time domain, we convolute their spectrums in frequency domain. Now, we also know that the cosine function can also be written as in exponential form as e power j 2 pi fct minus e power minus j 2 pi fct upon 2. The Fourier transform of cosine function is actually delta f minus fc plus delta f plus fc upon 2, where delta is a direct delta function. Let us assume that the Fourier transform of mt be mf. Now we know that xt is actually cos of 2 pi fct multiplied by mt, which is our message signal. So in the frequency domain, xf will be actually equal to mf convoluted with delta f minus fc plus delta f plus fc upon 2. Now we know that any signal convoluted with direct delta function actually shifts that signal to the value. So the xf will be given as mf minus fc plus mf plus fc upon 2. Now let us assume the spectrum of the message signal be something like this given in the first diagram. Here fm is actually the bandwidth of the message signal. Now from the frequency spectrum of xf, we see that mf minus fc plus mf plus fc actually represents the shifted version of mf. So the frequency spectrum of xf contains two peaks or two spectrums mf shifted at plus fc and minus fc. Now from the frequency spectrum, we can also observe that the bandwidth of mf minus fc and mf plus fc is actually 2fm. So we can conclude that the bandwidth of the DSBSC signal is actually twice the bandwidth of the message signal. Now, so what can we conclude from DSBSC modulation? That the bandwidth is actually twice the message signal. Now we know that the information is present in both the bands. So we can either use the upper band or lower band also. So if we can use the upper band or lower side band, we can actually double the number of users and we can use the frequency spectrum efficiently. Now the DSB signal can be coherently demodulated using the low pass filter. Now to use only the upper sideband or lower sideband, we make use of filters. Now here we try to get the upper sideband, so we are using a high pass filter. Now the high pass filter should have a sharp cutoff at a frequency fc. So for this high pass filter, the gain is actually 0 for frequency less than fc and the gain is actually 1 for the frequency greater than fc. Now the transition of the gain from 0 to 1 here is actually instantaneous, and this is not the case in practical filters. In practical filters, the transition from 0 to 1 is not instantaneous as seen from this diagram. So from here we can conclude that we are going to eliminate a small part of the upper sideband and we are going to include a small part of lower sideband, and this is what we do in vestigial amplitude modulation. We eliminate a part of upper sideband and we include a part of lower sideband. Okay, so what is the need of vestigial amplitude modulation? Now we have seen that for generating Vsb signal, it is very difficult to generate because of the sharp cutoff at Fc of the filter is not practical, and the double sideband suppressed carrier uses twice the bandwidth, so it reduces the spectral efficiency. Now to overcome these difficulties, we use vestigial sideband modulation, where we allow the unwanted part, here its lower sideband in our case, to be in the output of the signal. If we compare the bandwidths of the three signals, we conclude that the double sideband suppressed carrier has twice the bandwidth of the single sideband carrier, and vestigial sideband is in between the two. Now, for generating the Vsb signal, we make use of the DSB-SC signal. So, we have seen that the frequency spectrum is actually mf minus fc plus mf plus fc upon 2 of xt. Now, we pass the signal xt through our vestigial filter whose impulse response is given by hf, and the output is actually it, which is equal to xt convoluted with ht. Now, after passing through this filter, the output here is shown in the below diagram. Here we can see that we have added a part of lower sideband which is called as a vestige. So therefore it is called as vestigial sideband modulation. Now we know that yt is actually xt convoluted with ht. So in frequency domain we can write it as yf is equal to xf multiplied by hf. Now yt was actually the signal at the transmitter end. So at the receiver end we multiply yt with cos of 2 pi fct, and the output here is actually RT. So we can say that the Fourier transform of RT, which is RF, can be written as y f minus fc plus y f plus fc upon 2. Now we know that xf is given by m f minus fc plus mf plus fc upon 2. Yf is xf into hf, and rf is y f minus fc plus y f plus fc upon 2. Now here our aim is to calculate RF. So we have to calculate y f minus fc, which is nothing but x f minus fc into h f minus fc. X f minus fc is actually substitute f minus fc in f here. So we get m 2f minus 2fc plus mf upon 2 into hf minus fc, and yf plus fc is nothing but xf plus fc into hf plus fc, which is nothing but mf plus mf plus 2fc upon 2, which is written here. Now if we try to simplify this expression, we get m f minus 2fc into hf minus fc upon 4 plus mf hf minus fc upon 4 plus mf plus 2fc into hf plus fc upon 4 plus mf into hf plus fc upon 4. Now by seeing this equation, we can conclude there are 4 frequencies actually present. The first is 2fc, second is minus 2fc, the third is plus fc, and the fourth is minus fc. Now we try to get rid of these higher frequencies plus 2fc and minus 2fc by passing this signal through the low pass filter. So if you pass it to the low pass filter, our output actually will become mf hf minus fc upon 4 plus mf hf plus fc upon 4. Now if we try to get mf by 4 common, we get mf by 4 hf minus fc plus hf plus fc. Now for a time being, let us assume that hf minus fc plus hf plus fc is 1. So what we get is RF as mf by 4. Now if we convert it to time domain, we get RT as mt by 4. So we have retrieved our message signal completely. So to retrieve it completely, this signal, condition must be satisfied. So the impulse response HF must satisfy this condition that HF minus FC plus HF plus FC should be 1. Now let's see what can HF be. So this was our HF spectrum. Now we have the condition that HF minus FC plus HF plus FC should be equal to 1. Now F minus FC is nothing but shifting of this whole spectrum towards right by Fc. So if we shift this whole spectrum by right, this will go to 2Fc and this will come to the center. Now HF plus Fc is actually shifting this whole spectrum towards left by Fc. So this spectrum will go to minus 2Fc and this spectrum will come to the center. So if we filter the whole spectrum, if we filter the 2Fc frequencies, we get this resultant spectrum. Now we can see that according to the condition, they should sum up to 1. So this value is actually 1 and all these values should sum up to 1. So we can say that they should be symmetric around the y-axis, or we can also say that they should be symmetric around Fc. So if they are symmetric around Fc, by calculating the equation for this line, we can find the impulse response of the filter. So we know they are symmetric around Fc because they have to be means the summation of both of them, summation of the shifted spectrums, they have to be equal to 1. So from there we conclude that they should be symmetric around Fc. Now if we calculate the slope of this line, so we can get that slope is actually equal to 1 upon 2 delta f. Now the equation of this line then becomes f minus fc plus delta f upon 2 delta f. So the frequency response actually becomes 0 for f less than fc minus delta f, because the gain here is 0. The frequency response is f minus fc plus delta f upon 2 delta f for frequency lying between fc minus delta f and fc plus delta f, and the gain is actually 1 for frequency greater than fc plus delta f. So this is how we get the impulse response of the filter we are using in vestigial amplitude modulation. So this was all about vestigial amplitude modulation. Thank you for watching.